So I'm going to try and talk a little bit today about some work, not so much about this new project because we haven't started yet and we haven't done anything, so it will be a short talk. So we'll talk about some of the work I've been doing with a bunch of colleagues over the last number of years, partly focused on the weathering and alteration of volcanics. And I'm going to give, this is from the eruption in Hawaii from last week. And I work a lot in Hawaii. I'm going to give sort of four short stories or vignettes about some of the kinds of questions that we've been thinking about, and a few of the highlights of what we've learned. None of them are going to be in very much detail. Not everybody here really wants to get into the details of the geochemistry, I'm sure, so we won't do that too much. But hopefully you get an idea of some of the questions and some of the ways to address it. So the first one is really looking, and this is an aerial view of the lava flowing into the ocean from last week in Hawaii. So it's quite spectacular. The first one is looking at the large scale. One of the reasons we're interested in the weathering processes in general, and in particular the weathering of volcanics, is that the carbon cycle, the geological or long-term carbon cycle, we have something like 5 teramoles, 5 times 10 to the 12 moles a year of CO2 emitted from volcanoes, either at the ridges or the arcs or ocean islands. And if you take all of the carbon in the ocean atmosphere system, you find that the response time scale of all of that carbon reservoir is less than 1 million years. So in other words, we would double the amount of CO2 in the system every million years, and that clearly doesn't happen. And so for a long time, going back to the 19th century, people have recognized the need of some sort of feedback to limit that. And again, there's a long history to this idea, but one idea that's been very influential is that climate plays a big role because of the climate forcing of CO2. So it warms up, the climate functions, more CO2 goes in the atmosphere, it warms up, weathering rates increase because of that change in climate, and that stabilizes the CO2. And this is an idea that, like I said, has a long history, but actually testing it on the one experimental planet that we have has turned out to be more difficult than it really looks. Here's an example there's been much work on this problem. Here's an example of one study in continental settings on granitoids, looking at the chemical weathering rate as a function of denudation or erosion, mean annual precipitation, mean annual temperature. And you can see the climate sensitivity here is not extremely obvious in this data set, right? That's a bit of a problem because we have this very nice theory and lots of experimental work in the laboratory that says it should happen. And then when you go out in the real world, it's a mess, okay? And there are many studies that have addressed this, and in some cases the picture is clearer, in some cases not. But in general, continental settings, the story is less clear than we would have liked to believe. There are good reasons, again recognized for a long time, that arcs and other volcanic settings are good places for weathering and good places where you might expect to find this kind of process going on. So we have calcium and magnesium-rich silicates. That's important because the CO2 is removed as carbonates, and we don't make sodium and potassium carbonates in the ocean, hardly ever. We frequently resurface the areas, so we have fresh material to work with. This is the floodplain of a river in Pinatubo, and that's full of volcanic ash. That's why it's white, so that's going to be very reactive stuff. We have rapid incision and arcs, and a lot of these places are by definition near the ocean, so almost by definition they're usually wet, and that helps. So classically, when people started to look at global weathering, they went around to the biggest rivers in the world and John Edmund would say, well, you give me 1 bottle of water from the Amazon, I'll tell you what's going on in the world. And that's not a bad way to look at it because that's about 15% of the fresh water. But it turns out that we have this funny problem with these volcanic systems because they're often on islands or remote areas. There aren't any big rivers. Can you give me the name of one river in the Philippines, for example? And yet, erosion rates in these areas were known for a long time to be very high. They're also very wet. This is a runoff map, so these areas here are very wet, and so we would expect that they should be important. And in fact, it looks like, and this is based on work, lots of people, including here at IPGP, that volcanic provinces maybe account for 30% of global CO2 consumption, possibly more, even though they only represent a few percent of the terrestrial surface, the subaerial surface. And that may even be a bigger underestimate than we thought, because much of the water from those areas goes to the ocean via direct groundwater recharge, which is something you can't really see. This is one of the few images. This is along the west coast of the island of Hawaii, and you can see the scale is pretty small there. And this is a thermal IR map, and you see the cold groundwater entering into the warm ocean on the coast there. And when you go to Hawaii, everybody knows about these because the groundwater temperature is much colder, so all the divers and snorkelers know. And when you cross into one of these plumes of groundwater, it's much colder and you can't see anything because the refractive index is different and the water gets all shimmery. So the divers don't like it. But anyway, we were able to do some work on that, and we found, to our surprise, we did a lot of work measuring streams. We found, to our surprise, and we looked at alkalinity, which is a measure of CO2 consumption, and silica discharge into the ocean. There was about 15 times more flux from groundwater in Hawaii than there was from stream water. So we did all this work measuring streams, and that was 6% of the total flux. It was interesting, but it was sort of pointless, right, in that sense. So groundwater has hardly been measured in these places. So that's one of the results that we came up with that suggests that the fluxes are even larger than we thought. But if you go to Indonesia or the Philippines or all these places, there are essentially no data. We're sure it's there, but we're also we're sure we don't know the numbers. So this is a summary of a lot of work. And with Gaojun Li, we took a bunch of data from all the data we could find from almost 40 different places where there are volcanic rocks. The red ones are volcanically active, and the blue ones are no longer active. And we looked at a number of things, but just in summary, we looked at that as a function of temperature and runoff. And so if you separate out the active from the inactive fields, there's a pretty good relationship between weathering rates and the inactive fields and temperature. The active fields are high. You probably have hydrothermal alteration. So the effective temperature is the temperature of the hydrothermal system, not of the climate. So they don't follow the same relationship very well. The relationship with runoff is a little messy, but and that may be a function of not correctly including groundwater fluxes, because that may be a big role there that we don't have a good handle on. If you fit this to some sort of Arrhenius law, you end up with an activation energy of about 42 kilojoules per mole. That gives you a climate sensitivity, what a biologist calls a Q10, where the weathering rate would about double for a 10-degree increase in temperature. And this is consistent with earlier studies, including ones that Jerome was involved in here, but it suggests that the feedback between climate and weathering, at least in these volcanic provinces, ought to work in about the way we expect from laboratory experiments, where it's not so clear in granitic systems, right? The controls, temperature and precipitation play a role for certain in continental systems, but it's substantially involved with erosion rates and things like that, making it difficult to separate. So we don't need the whole world to follow a simple relationship like this. But it does help if part of it does. And so that says the carbon cycle can be, these kind of rocks can play a substantial role in stabilizing the carbon cycle over time. We don't need the whole world to show this kind of relatively simple climate sensitivity. And so that's on a very large scale, and that's the summary of many studies, but we want to know a little bit about how this works, right? And so we can kind of dig in a little more detail at a smaller scale. So Hawaii makes a really good natural laboratory for this. It's quite high, it's 4,000 meters high. The trade winds are very strong from the northeast, very regular. So we have a very pronounced climate gradient, very wet on this side, up to 7 meters of rain a year, and very dry on this side, as little as 20 centimeters of rain in a year. So you go from 4.5 meters of rain to 20 centimeters of rain, just that far. Very striking. And of course you have the active volcano down here, and so you have everything from this morning's lava flow to about 450,000 years out there as the plate motion is in this direction, right? And so we can pick what climate we want, we can pick what age surface we want, and we can extend that over the whole Hawaiian island chain out at least as Kauai if we need to. So here's a rainfall map, and this is a geologic map, so you can see the very young stuff from Kilauea and recent Mauna Loa, older Mauna Loa material, and Mauna Kea and Kohala here. And so this gives us some idea of what you're looking at. So as I said, we can extend this out onto some of the older islands. There's still some of these surfaces available, even out at Kauai, 4 million years old. So it's a good system to work on, and it's also a nice place to go. So this is a series of sites that were developed by Peter Bertusik and Oliver Chadwick initially, and these are all picked for the same elevation, same rainfall, same vegetation, but an increasing age of substrate from about 300 years to 4 million years. And so the age is plotted on a log scale here so we can see something. And so what we're seeing here is the depletion of potassium, magnesium, and calcium with age. You can see at the earliest ages it's almost all there, and by about 20,000, 25,000 years, the soils have become almost completely depleted in these elements. We also lose aluminum and phosphorus and silicon, and then this is just an indication of the kind of clays that are formed. So this very, very strong weathering depletion is fast there. It happens in 10, 20, 30,000 years because of the climate is favorable and the rock types are favorable. So I'm going to show some data in this form. I just want to explain what a graph like this is trying to tell us. This tau function, or mass transfer coefficient, is just the normalized concentration of an element relative to some element that we think is immobile, that isn't lost by weathering. In Hawaii, almost everything is moved around by weathering. We did a lot of work trying to figure out what was the best element. It turns out niobium and tantalum are the best ones to use, and so we normalize everything to niobium there. So that's the mass transfer calculated relative, for some element calculated relative to niobium, which appears to be stable. So if you look in the upper, and so if that number is 0, there's been no change. If that number is -1, it's 100% loss. If the number is positive, there's been addition. So if we look at, let's say, calcium, and this is a 5-meter deep soil profile dug with a machine, a backhoe. I don't know how you say backhoe in French, but one of these excavators, right? And in the top meter or two, the calcium is almost completely lost. The silicon is 70 or 80% lost. Even aluminum, which is usually considered not very soluble, 50 or 60% of the aluminum is lost. We see the aluminum added back in at depth. So it's being transferred from here and then reprecipitated down there. So that is the kind of pattern we see in a lot of these soils once they begin to weather. So it turns out Hawaii, like many places that are in these kind, is very heavily vegetated. Even the cliffs are vegetated. And so the vegetation plays a really big role. There's a lot of organic carbon in the soils, and it plays a really big role in the weathering processes. One is that the decomposition of that organic carbon in the soil gives very high soil CO2 levels. So these are the points are data from gas samples taken from the soils, and the blue line is just a reaction diffusion model calibrated with the emission of CO2 to the atmosphere from the soil surface, and the red line is the calculated production rate. So you can see we get up to 15 times atmospheric CO2, or like up to 5,000 ppm CO2 in these soils. So that means that makes weathering processes go a little bit better because CO2 is providing the acidity for this. And if we look at the pH in these soils, this is a quantity called a soil pH, which is a little bit different than a solution pH, but anyway, the trends are similar. And so what you can see in the young soils, less than 10,000 years, that still retain their calcium and magnesium to some degree, you can see the surface soils are acidic because there's lots of CO2 there and they're leached. But as we go down, the pHs get buffered towards neutral values because the CO2 is consumed and buffered by these alkalis and alkaline earths. But once those are gone in the older soils, we don't have any calcium, magnesium, potassium left essentially. Then the pHs are much lower, and the soil pHs are buffered by surface interactions with iron and aluminum minerals. So they're much more acidic. And if we actually go collect water from some of these and just measure the pH, we get pHs as low as 3.7 or 3.8 in the soil water, which is quite acidic. So one of the things that we've done, in addition to collect a bunch of data, they're complicated systems. So by using reactive transport models, we can test how certain hypotheses should play out and compare it to the observations. And so a reactive transport model models the concentration in the solution as a function of the transport and of the reaction. And the reaction is driven ultimately by thermodynamic disequilibrium, controlled by some approach, some rate law that controls the rate at which you approach equilibrium. And that's partly a function of disequilibrium and some reaction rate constants. And this is a sort of a standard transition state theory approach. So the reactive transport model solves for a bunch of different components all at once. And then it solves the chemistry, moves the fluid, does the chemistry, moves the fluid, does the chemistry, move the fluid. It's a good job for a computer. This is, we use just a linear transition state theory model for this. We have olivine, clinopyroxene, plagioclase, and volcanic glass. And then we have to precipitate secondary minerals. And that precipitation rate is modeled as a function of the saturation state. Obviously it's undersaturated, it won't precipitate. If it's strongly oversaturated, it'll precipitate faster. And this is based on some experimental work in this case, by Yang and Stiefel. The secondary minerals there, the ones that I'm going to focus on just for now, the aluminosilicate ones are these funny little poorly crystalline or nanocrystalline materials called allophane and amogolite. They're sort of like kaolinite, but they have a little bit different stoichiometry, and they're not crystalline. If you X-ray them, you don't get anything. You just get mush in the X-ray pattern. But this reaction, the equilibrium of this reaction is controlled by the activity of silicon solution, of aluminum, and strongly by the pH. It's cubic in the hydrogen ion concentration. So pH is a big control. So what I'm going to show here are some of those diagrams. Again, we're looking at that tau, that depletion index for iron and aluminum here, and pH. And these are for 3 different points along that age gradient. The 300-year-old material, which is very weakly altered, the 10,000-year-old material that has started to alter more significantly, and the 20,000, 25,000-year material, which is altered quite substantially. So, and then the 3 curves are model simulations. In this case, we used about a maximum CO2 of about, I think, 3,000 ppm, and of course the CO2 is highest deeper down and low near the surface because it diffuses out. And we try to see if we can get these things right? And it turns out if we put in enough CO2, we can get the calcium and magnesium to go, but we don't do such a good job with some of the other parameters. You can see our pHs are too high because the CO2 gets buffered, and you can see aluminum here. According to these simulations, aluminum is doing nothing. And all of the simulations plot right on top of one another, and yet at 300 years, aluminum really is doing nothing. By 10,000 years, it's moving. By 20,000 years, we've lost a lot of aluminum. So we're completely missing on the aluminum, even though we have 3,000 ppm CO2. Why is that the case? At 3,000 or 4,000 ppm CO2, you can see we're undersaturated strongly with respect to pyroxene, plagioclase, olivine. This is a proxy for, this is the glass composition. So all of those become strongly undersaturated and they dissolve as they should. But the secondary minerals, these aluminosilicate nanomaterials, allophane and amogolite, we remain essentially at saturation with those. So what happens is we dissolve the aluminum out of the glass and we immediately precipitate it as a secondary mineral, so it doesn't go anywhere. Okay? So clearly we got to do something about that because it's giving us a bad answer for aluminum and a bad answer for pH. Turns out that with all that soil organic matter, we have a lot of other compounds in there, and so there's good experimental work on this, on looking at some of these simple organic acids that occur in soil solution. And we put in citric acid and oxalic acid into our simulations. They both affect the pH, and they also complex with metals. And so we wanted to see what the effects of those would be. And they're pretty simple to work with. Hard to measure in the field, though, because they turn over very quickly. So with reasonable levels of oxalate and citrate, we run the simulation again. This is just an example, and actually things come out much better. Our pHs are down where they should be. The aluminum is beginning to move in ways that are much more realistic. And with the reactive transport models, there are many, many parameters you can play with. So you can make the model fit if you spend enough time twiddling the parameters. I don't think that's really the point. Right? The point is, can we understand the process behind it? And yeah, we can make it a little bit better by adjusting the parameters, but I have 100 parameters in this model to adjust at least. And if I can't get it to fit with 100 parameters, I should have a different job, right? Doesn't mean it means anything. So I'm not trying to make it perfect. Because if you see a reactive transport model that's perfect, you should be instantly suspicious. Okay? Except when Nicole does it. So, because there's a lot of adjustable, but anyway, we're moving in the right direction here. And so what this tells us is that if we want to get the chemistry right, there's a strong indication that the organic compounds play a significant role. And here's a little bit about why. If we look at the total dissolved aluminum in that 20,000-year-old site, you can see it's about 10 to the minus 4 concentration. But the actual aluminum ion that would precipitate to make the clays is several orders of magnitude lower, and that's because much of the aluminum in the presence of these organic compounds is actually complex as either citrate or oxalate complexes. So it lowers the aluminum activity, the effective thermodynamic concentration of the aluminum 3+, therefore inhibiting the precipitation of these secondary clays, and so the aluminum can leave as opposed to immediately reprecipitating. So it's an interesting way in which the biology can impact the weathering process. So this is the kind of environment we're working in there, so there's plenty of organic matter. By the way, this is where Jurassic Park was filmed. So you get a little nervous when you're out there. You know they're not supposed to be any dinosaurs in Hawaii, but you get a little nervous sometimes. So anyway, one interesting idea with this is people have looked at paleosoil profiles, ancient soil profiles, to try and understand atmospheric composition in the past. And so mostly they're focused on oxygen and iron, a little bit on CO2, but it might be interesting to look in more detail at these insoluble elements, and if they're moving around, it's probably telling you something about terrestrial vegetation and whether you had organic matter on the Earth's surface, certainly after the Silurian, but maybe you had microbial mats or other things like that earlier that impacted weathering processes prior to the development of vascular plants. Okay, so the next thing I want to do is think a little bit on a landscape scale. So Hawaii is an interesting place because although if you look at the precipitation, it's high all along here. In this part of the island, on Mauna Loa and Kilauea, there are no surface streams. There are no permanent streams there, even though you have up to 5 meters of rain a year. And this is groundwater recharge, so all the water that lands there either goes back to the atmosphere as transpiration from the trees, or it goes into groundwater. 100%, there's zero runoff, essentially, despite 4 or 5 meters of rain a year. If you go on the Mauna Kea surface, which is, let's say, 20 to 100,000 years old, you start to get a stream network. It's still a simple network. You have very many sort of parallel streams that don't branch very much. And then if you go to the oldest part of the island, you start to get a more traditional Hortonian branching network. So there's a strong control of age on the landscape evolution, and it makes sense that maybe weathering and soil development has something to do with this. So I tried early on with one of these reactive transport models to weather the soil, make a lot of clays, stick up all the pores, and that would solve the problem. And it didn't. It failed because I can't reduce the permeability, the hydraulic conductivity sufficiently to get that to work just from weathering alone. So here's another example of, this is out in the oldest part of the island. You can see these giant 1,000-meter deep canyons that are incised into the landscape. This is in the Middle Age part. And part of the problem, this is a lava tube, which is now a stream channel. So I don't know what the hydraulic conductivity of this lava tube is, but it's pretty high. So it's no wonder we don't have a lot of stream runoff because the initial porosity of the volcanic system is very, very high. Okay, the density of the lavas near the surface is often around 1.5. The density of basalt, of course, is 3. So it means half of it is porosity just from the beginning, right? And you have lava tubes and all that stuff. So it's a problem to get the permeability and hydraulic conductivity down low enough that you actually get surface runoff. And it's a big transition because once you make a stream channel, then you collect the water and the process advances. But getting there in the first place is not obvious. So here's some example of the deeply incised topography here up in Waipio and Pololu valleys. This is a pretty nice place to go. And so here's another view. This is, instead of doing sections along stream profiles, this is lateral sections. And so this is what the topography looks like as you transect along 500 meters and 200 meters elevation on Mauna Loa. Essentially, you're just seeing the constructional volcanic topography, no incision there. This is along Mauna Kea where you start to have a stream network, and so you incise up to 50 or so meters, maybe a little more there. And then this is out at Kohala where you have the big landslide escarpment, and then you have the upper profile is at 500 meters, and so you have almost 500 meters of relief there. You have over 1,000 meters of relief on Kohala, and quite spectacular. So anyway, there's some observational data that tell us, yes, the hydraulic conductivity is going down. This is a site-based study from a field plot using a Van Ganukten type model for the deeper soil horizon. And in the young soil horizon, the hydraulic conductivity is very high, and in the older soil horizons, it does go down by quite a bit. All right, so okay, that makes sense. And this is a watershed level calculation. Is this thing working? Yeah. Yeah, oh, it's just not very bright. Where you can estimate the hydraulic conductivity from watershed characteristics. And again, it shows us the older sites, the conductivity is getting lower than in the younger sites. Makes sense, but the question is, how does that work? So we still don't really know the answer, but this is something I've been working on just recently, and maybe some people here who know more about solid mechanics than I do can help me out. But there's an interesting model, a porous plastic model, this paper's been cited more than 3,000 times, so it's popular in the material science literature, and this is, I simplified the equation for the isostatic case here, but essentially this is the plastic limit, and that's a function of the void fraction of porosity, F, and also the intrinsic strength of the material, right? The yield stress of the remaining material. And this is the isotropic stress that would be applied to it. So this is a calculation where you can see as the porosity increases, the yield limit goes to 0 at infinite porosity, at 100% porosity. Obviously has no strength. That's good. At least it does that. And this is, so we're increasing porosity as we go this way on the x-axis. And then these curves are calculated for different fractions of the initial yield stress of the material. So as we weather the material, we turn it from basalt, which is relatively strong, we turn it into soil, which is relatively weak. And so I can calculate that empirically based on how much mass loss has occurred, how much material I've lost from that, how much calcium and magnesium and silicon I've lost from material. And this is just, rather than show that in any detail, this is just showing at 100% strength at 50, 25, 10. And so as you weather the material and as you increase the porosity through weathering, you both weaken it and increase the porosity, and you get down where the yield stresses are only in the order of a couple hundred kilopascals, which are the same range of what you'd expect from thermal stresses or from wetting and drying stresses, or possibly there are earthquakes periodically in Hawaii. Maybe every 10 years there's an earthquake and it shakes it. I don't know the answer to that, but we don't have large stresses there because we're only within a meter or two of the surface. So this is something that, again, sort of some exploratory stuff to try to think how the chemistry can affect the material properties so that then we can then affect the hydrologic properties as the soil collapses. And what we do is we see that this is our mass loss indicator. The enrichment of niobium as all the other elements leave. Niobium is left behind and therefore it's enriched. We haven't added niobium, we've just taken everything else away. And you can see that can be up to more than a factor of 10 depletion in the mass of everything else. And if you look at the dry bulk density, which is sort of a poor parameter, but it's available, you can see that the density decreases as we develop porosity by weathering. And then around the right age, the soils begin to collapse and become more dense again. So the hypothesis is weathering is weakening the material through the creation of porosity and the transformation of the material properties from basalt to soil, which is weak. And then with time, it begins to collapse. And then we should reduce the hydraulic conductivity. We get lateral flow. We can begin to have incision. And so it's a real bifurcation point in landscape evolution when we reduce the hydraulic conductivity of the system sufficiently that we can have stream channel development. And this may be a way in which that happens. It's still a early stage hypothesis, and there may be other good ways to do it. Finally, the last thing I want to come to is to switch gears a little bit and think about what I call the Earth's other critical zone, the interaction of seawater and the oceanic crust. And this has been worked on a lot from a lot of different perspectives. I'm going to focus on the off-axis or low-temperature alteration of the oceanic crust. And that's basically known from heat flow arguments. Here's the red are the predicted conductive geotherm that you'd expect from a half-space cooling model. And these are the observations that show that you've got a deficit in heat flow. This is a way of expressing that deficit. This is from a recent paper by Hasterrock. And so that deficit is presumed to be made up by hydrothermal circulation, and that's how we estimate global hydrothermal circulation off-axis. How actually other geophysicists have estimated that. I don't do these calculations myself. I read their papers. So anyway, it turns out that about although the black smokers at the ridge axis, the 350-degree fluids, are spectacular, they account for the off-axis hydrothermal flux is thought to be about 70% of the total hydrothermal flux to make up this heat deficit. And it continues out to about 65 million years, at which point the half-space cooling model begins to agree well with the observations. But for the first 20 or 30 million years, it continues to be pretty active hydrothermal circulation at much lower temperatures off-axis. It does a lot of interesting things, and people here have worked on that. The thing that I got interested in is the effect on iron oxidation. And this is data from DSDP Site 504B, where they drilled into the oceanic crust, one of the first ones that did that and got good recovery. And what you can see is that the iron 3 to total iron ratio increases as you come to the surface. So that initially, the Morbs have an iron 3 to iron ratio of about 0.16, and with time that increases because of this oxidative alteration up to around 0.4, 0.5, depending on where you are. The first really good paper on this was Lecuyer and Ricard in '99 and Bach and Edwards in 2003. And so we're oxidizing, we've got oxygen in seawater, it gets pulled into the upper part of the crust, it reacts with iron-bearing olivine and pyroxene, and it reacts with iron sulfides in the oceanic crust. And so mostly it's confined to the upper few hundred meters where the permeability of the oceanic crust is high. The oxidation and reactions mostly are limited to the upper 300 to 500 meters. And they consume about 0.7 teramoles of oxygen equivalent per year, which is about 15% of the oxygen that's made every year by burying organic carbon. So the interesting thing about this is the mantle, by providing the sort of infinite reservoir of reduced iron to the surface, is taxing the redox system of the planetary surface at about a 15% rate. And that's about what you pay, right? We're all used to this sort of 15% tax rate plus or minus, right? So you get the idea, right? And it's just like taxes, you can't avoid it, right? So, because the mantle is always making new oceanic crust every year, and so it's always supplying new material. So it's an interesting thing to think about, and how that might have evolved through time. So again, we can answer this question in part by comparing models to observations. So you take a seawater composition, you take a basalt composition, you let them react, and so I'm going to do two experiments here. One, I'm going to use modern seawater and see how it works in the modern system or experimental system, and then I'm going to use seawater, supposedly ancient seawater, without dissolved oxygen and with low levels of dissolved sulfate. So this is experimental data that is a nice system to compare to. So this is the experimental results from reacting basalt and seawater for about half a year. This is old data, but it's still good. And this is what the experiments gave, and this is what the simulations gave. So I'm like, okay, this approximately works. I'm not too unhappy about this. And then I can do this over different water-rock ratios, different temperatures, different seawater compositions, different amounts of time. And you see the basaltic glass reacts and goes away here, and I produce all these secondary minerals. And in the modern oxygenated system with about 100 micromolar dissolved oxygen, what we might have in the deep sea, or 150, what happens is the iron dissolves, but the iron immediately oxidizes and makes iron oxides, and so the dissolved iron levels are nanomolar level. All of the iron is immediately precipitated out as iron oxides, in some cases as iron clays. So there's essentially no dissolved iron in these fluids, and there's essentially no dissolved iron in seawater. It's all there as either colloidal particles or things like that, but not truly dissolved. It's too oxygen rich. If we do the same thing with seawater without oxygen and at low sulfate levels, we make iron 2 clays instead of iron oxides because we don't have the oxygen to make the oxides. And the dissolved iron levels can be much higher. Instead of nanomolar, we're up there at half a millimolar. In other words, 6 orders of magnitude higher. And so the iron is coming out of the basalt, but it's not being precipitated out, and it can be exported out of the oceanic crust into the water column. So that has some interesting effects. And one of the things that I found, and this is one of those results that's interesting if true. All right, this might be, it's a model result, and it may be somewhat misleading. Anyway, if I look at the iron, the axis you can't see, this is the iron 3 to total iron ratio. The initial basalt is at 0.16. Under oxidizing conditions, I increase the iron 3 to total iron ratio just like the observations in the modern oceanic crust behave. But if I don't have oxygen, I actually decrease. I'm actually reducing iron 3. well, that doesn't make any sense. What's going on here? What it turns out is, okay, what it turns out is that under oxidizing conditions, the redox state of the fluids is essentially buffered by the fluid because it carries enough oxygen until that oxygen is exhausted. But under anoxic conditions, there's no oxygen in the fluid, so the redox state is controlled by the basalt, and the basalts are essentially at QFM. There's been a lot of work on that by petrologists to show that morbs are quite close to QFM. So what happens in this case is the fluid, it's a rock buffered system, this fluid wants to go to QFM. No one ever does this and calculates what QFM looks like at 25 degrees C, because why would you, right? Nothing happens interesting at 25 degrees C if you're a petrologist, right? But in fact, the oxygen fugacity at QFM goes down and down and down as the temperature goes down. So the oxygen fugacity at QFM at 25 degrees is around minus 70 log units. So the thermodynamic drive is to reduce the iron. Now, whether this actually happens in real life or not is unclear. So that's an interesting thing to maybe do in some experiment, because we don't have rocks like this to look at today where we are altering the oceanic crust with oxygen-free seawater. So it may be a red herring, it may just be wrong, but it's an interesting observation. And so the reason why there are a couple reasons why this is an interesting question, but one is the iron-3 to total iron ratio in arc rocks reflects the oxidation of the oceanic crust. Those arc rocks have a lot more iron-3, and this presumes comes from altered oceanic crust that's subducted. If we don't have any oxygen in seawater, we'd either predict that there'd be no change, which is the default hypothesis, or if the calculation I just showed you makes any sense at all, which maybe it doesn't, we might even reduce, these arc magmas might even be more reducing than they are in the absence of oxygen. So that's just an idea to throw out there. There are some data. I gave a talk about this last year at Goldschmidt, and at the same time, Dan Stolper and Brendan Keller, one of our former students, put together this data set. They gave a talk at almost the same time, and they actually compiled the iron-3 to iron-2 ratios in subaqueous volcanics through Earth history, and they published this earlier this year. And they show that, yeah, when you go back before about 500 million years ago, the iron-3, iron-2 ratios in the basalts that they could get out of the literature were all near the magmatic value, and they only show increasing iron-3 oxidation essentially in the Phanerozoic. So this is a biased data set because you're not going to find normal oceanic crust in the Proterozoic, right? Or if you did find it, you probably wouldn't even be sure you had it. There are ophiolites, but you don't know where they came from exactly. But it's an interesting set of observations. And the other thing there are a bunch of interesting biogeochemical implications of this too, which is a whole nother talk. But simply say this, that we're essentially moving the planetary redox boundary out of the upper oceanic crust. And if deep water was anoxic in the past, which we're pretty sure it was for significant parts of Earth history, we're moving that planetary redox boundary up into the water column. And so instead of iron being oxidized in the oceanic crust, it's actually being exported out of the oceanic crust and oxidized in the ocean itself. And there are many interesting biogeochemical impacts of that, one of which is the way that ferrous iron and phosphorus interact. And I've written a paper about this as Tom Laxo and Dan Schrag with a little bit different approach, where the presence of that ferrous iron can suppress phosphorus levels in the ocean quite substantially, therefore limiting marine primary production, therefore limiting organic carbon burial, and therefore limiting the growth of oxygen for a long time. So this may be, if we speculate here, this may be the kind of mechanism that maintained relatively low oxygen levels in the atmosphere, let's say through the Proterozoic, after we had some oxygen in the atmosphere, like James has shown us, right? But before oxygen levels got very high. So this may be a mechanism to do that. But anyway, this evolution of the alteration process is an interesting one that we can approach with a similar kind of tools that we can use from modern basalt weathering. So anyway, that's the last of my 4 vignettes, right? And each one of these is a short story without too much detail. Quick summary there. And this is Volcan Fuego in Guatemala. My brother-in-law, this is from my brother-in-law's house. And fortunately, he doesn't live where the Lahars are. He lives across the valley. But we were there at Christmas 2 years ago, and the volcano was already erupting. So this is Christmas morning on the roof of his house. And it's quite a different way to spend Christmas than I'm used to, but it was kind of fun. Anyway, we were far enough away that, the wind was blowing in the right direction, we were okay. But anyway, thanks for your attention, and I'm happy to answer any questions if I can.
Okay. Questions, comments? Des questions, des commentaires? Allez-y. Oui.
I have two questions. One is how can you estimate the groundwater's flux? Because you said it's an important flux.
Yeah, so essentially the groundwater flux is estimated with a water budget model. So precipitation minus evapotranspiration minus runoff. So the USGS has done this a lot. The uncertainties are relatively large. What we find on the island of Hawaii is the groundwater flux is approximately 4 times the stream runoff from that island because it's young. And when we look at the chemistry by looking in wells and springs, we get about 4 times as much silica as about 4 times as much alkalinity. So 4 times 4 gives us 16, and so that's where that estimate comes from. But measuring groundwater flux as well is very difficult. So these water budget models have large uncertainties. They get better, but in fact, as far as I know, this is the only place where this has even been done. So all these other places, there are no estimates of groundwater. I'm sure it's there, but we have 0 estimates of it, as far as I know.
And I had another question about aluminum in the soil profile. You said that aluminum was mobilized by the organic matter, but and then how is that enriched? You did not in the deep part of the soil.
We don't know for sure. What we suspect is that microbes are eating those organic compounds because those are good microbial fuel. They're small, low molecular weight organic molecules that can be accessed by the microbial community. So we think that might be the case, and a number of plants and microbes will actually secrete those oxalate or citrate to detoxify their environment in the presence of high aluminum. You can feed back some of soil bacteria, these pseudomanads, you can feed them aluminum and they will exude oxalate to detoxify the system because it badly impacts calcium metabolism. But some of the heterotrophic organisms we think are actually consuming these organics, and therefore then the aluminum becomes available and reprecipitates. But we haven't demonstrated that yet.
Thank you.
Okay. More questions?
Hi. What about iron microbial cycling in the first kilometer of the oceanic crust in your last models?
Yeah, well, there's lots of people that are working on that who know much more about this than I do, but very likely one of those papers, what they were trying to do is calculate the total amount of iron-3 generated because, and they were interested in the microbiology because they wanted to see if that would produce metabolites that the organisms could use, right, the iron oxidation. So very likely a lot of that iron oxidation in that upper few hundred meters, that's where the water-rock ratios are high and the permeability is good, probably a lot of those reactions are actually carried out by microbes, right, because they've got, if there's some organic matter there, they can use that oxygen or iron redox couple, right, so that may be that the kinetics may well be controlled by microbial reactions. And in Hawaii, in the soils, we have a lot of iron redox chemistry going on there. I didn't talk about that, but there, the soils get wet, the soils turn red, and then as they get wetter, they turn yellow, they turn tan, and then they turn gray. Because as the soils become saturated, there's a lot of organic matter in there, the microbial community switches from using oxygen as the electron acceptor to iron-3 because they're very iron-rich. And then the iron-3 is reduced to iron-2 and it goes away. So the soils change color dramatically over a short distance when you reach a certain water threshold. So I'm not a specialist in microbiology, but that is a very interesting process that is very important there.
Thank you. More questions? Comments? Jérôme.
If you thinking about the citrate oxalate, changing the mobility, changing the porosity, how should I think about that if I go back in the past?
That's a good question. Now, as you know, people have worked on paleosols and looked at iron loss as an indicator of whether the atmosphere was toxic or not, and looked at, tried to estimate CO2 levels from the degree of alteration. And I think it would be worth revisiting some of those data sets and look at these metals, which are supposed to be immobile, and see if they're moving around or not. And what we are seeing here, when we have a system where we have 4,000 ppm CO2, we have that, right? And when we try that in the simulations, we don't get the aluminum to move. And we also see movement of even things like zirconium and thorium are also depleted in the surface soils, and they should be really immobile, but we're almost certain that's either moving as colloids or as organic complexes, right? So it would be interesting to look at some of this paleosol data and see if, let's say, pre-Devonian, you had evidence for the role of organics and the evidence would be indirect. It would be, are we seeing mobility of these so-called immobile elements? And at least so far, we haven't been able to get them to move in any significant way, absent either very strong acids like dumping sulfuric acid on it because you're right close to the volcano, or by adding these ligands, which can complex them, because the acidity from CO2 alone, we can't get the pH low enough. Even if you have 1 bar of CO2, you can only get the pH down to 4. It's as low as you can go, right? And we're seeing pH is lower than that, so right away we know something's up, right? And we're not, on those sites, we're far away from the current volcanoes, so the sulfate inputs are quite low today.
How do you know that niobium was immobile? Because, as you said, all the immobile elements.
It's a good question. So we went through the periodic table and picked out all the elements we thought might be immobile, and we measured them all and we ratioed them all up, right? And what we found is that niobium to tantalum ratio was about 16 in everything we looked at: fresh basalt, young soils, old soils. Even though everything else was changing, niobium tantalum ratio was always basically the same. So either we're really unlucky and under all these different conditions, niobium and tantalum are moving in exactly the same way. I don't think that's right. Or they're basically not moving. But if you look at the ratio of zirconium to niobium or thorium to niobium, you see movement. But yeah, we were lucky because if we only had one, we wouldn't have been able to do anything. But fortunately, tantalum behaves the same way. Niobium is more abundant, so we use that because it's easier to measure.
So Lou, you've been working in Himalaya on carbon burial as a CO2 sink, but you didn't say a word on that process in Hawaii. What is going on in Hawaii for organic carbon burial?
I think that there's probably some organic carbon burial going on in the sediments off of Hawaii. We haven't done any work on that. The soils are quite rich in organic carbon, but it turns over relatively quickly. Although the soil carbon in Hawaii can be old, up to 10,000 years, right? So for a soil carbon person, that's very old. For a geologist, it doesn't mean anything. That appears to be stabilized by the interaction of that organic carbon with these mineral surfaces, these secondary mineral surfaces. So for example, when we see the soils lose iron, the radiocarbon age of the soil organic matter gets much younger. So what we think is that the iron complexes are playing a key role in stabilizing that organic carbon, and when it gets wet enough that the iron begins to be reduced and removed, then we're turning over the carbon much faster. How much of that is buried offshore in sediments, I don't really know, and that would be interesting to look at, how much of that material survives the trip. So we don't know the answer to that.
Hello, the basalt is really high in porosity to start with. With continuous weathering, you talk about the more pores to develop. Eventually it will collapse. But how does the reactive transfer model accommodate that volume change? If not, how can you compare the model results with the soil profile directly?
Yeah, it doesn't. When we run these simulations, there are changes in porosity that the model predicts. But as I said, they're not sufficient. So you're right. In fact, we can tune each simulation a little bit to agree with the actual observed porosity for that system. It's kind of a little bit cheating. So you're right. This is a problem because the reactive transport models don't have the capacity to do mechanical deformation at the same time. That would be like the model of everything, right? This is hard enough already. You've got to So you're right. So I think we're probably overestimating. If we start from time zero and run the model forward 100,000 years, by 100,000 years, we're very likely dealing with a system where we've overestimated the porosity and overestimated the hydraulic transmissivity, and therefore sort of underestimating the residence time a little bit. You're correct, that's a problem. I don't know how to solve that yet, but ultimately you would need to couple mechanical deformation with the hydrologic transport and the chemistry. So that'll be crunch flow version 3, right?
Okay, more questions? Comments? If not, okay, great.
What sort of ages do you actually have in terms of the water in your aquifers in Hawaii? Is it an old water aquifer system where you're... Okay.
We don't know the ages, and that was a really interesting question, because we know in some cases we're seeing transport probably on a vertical scale of maybe up to 1,000 meters, because we see seeps coming out of these deep canyons where the water chemistry is very different than the river chemistry. It's probably percolated down. We know it's sort of beyond the tritium age scale or the CFC age scale, but beyond that we don't know. Is it 50 years, or is it 500 years, or is it 5,000, or is it 50,000? We really don't know the answer to that. So for some of the shorter pathways, it's reasonable that the transport timescales are decadal or something like that. But for these long transport pathways, we don't have an estimate in that. And if you know how to do that, that would be really cool.
It's not quite my area.
Okay, more questions? Comments? If not, let's thank the speakers once again.
Thanks.